Okay, thank you, Juan.
Thank
All
you.
right. So, um, my goal is to get you all excited about strict reverse math uh, with these talks, and let's see how good a job I can do. Um, Now, a considerable portion of these two talks is based on this manuscript on my website, The Emergence of Strict Reverse Math. I talk about the history of regular reverse math as well. And from the work that I've done on this talk, uh, there will be some serious revisions to this document. Uh, so uh, stay tuned for that. Uh, so this first talk focuses on SRM, which is obviously an abbreviation for strict reverse math, for what I call omega-based countable mathematics. Omega-based countable mathematics is the bulk of what RM is addressing. By omega-based, I'm distinguishing it from general countable mathematics, or if you want to talk about this from the point of view of logician, something like HC is not what reverse math is really doing. It's all based on the current reverse math, and mainly is based on uh, subsets of omega and coding over such things through the subsystems of Z2. Um, so in the second talk, I want to talk about SRM for integer Z-based finite mathematics, Z-based finite mathematics. And instead of fragments of Z2, fragments of Z1 is more relevant, and Z1 is PA. And then I also want to talk about some about the reals-based, R-based analysis, where that's script R standing for the real numbers. And this is an entirely different this is a different situation entirely. All right, so here is some the list of topics I want to cover today. First of all, the origins of strict reverse math might be of some interest to you. What does strictly mathematical mean in the first place? Uh, and I want to talk about SRM for Z2 fragments. So how do you do SRM for Z2 fragments? What is left to do? What is the point? And then there's this more open-ended part of SRM that I want to talk about. So I call it SRM for the wilderness. Here, we're anchored in these already formal systems that we have and love. And here we're not anchored in such things. I call this the wilderness. Now, then I want to talk about the system ETF, which it's the founding system of SRM. And this is introduced in Friedman 76, the paper, the abstracts in 1976. We want to talk about this system in detail and some projects involving some specific projects, some specific yes/no projects for ETF, as well as some open-ended, more expansive questions. Um, and then I want to just talk about how SRM works for how does it work for these systems, these five, um, RCA naught, WKL naught, ACA naught, and Pi 11 CA naught, and ATR naught. Notice I shifted the order between these two. There's a reason for that because there's a more delicate point that's needed in order to do the SRM for ATR naught. Um, Okay, so let's begin with this. So my original conception of RM was really what I now call strict reverse math. my original idea was a very strong form of strict reverse math, even stronger than I can possibly back up today. Uh, and then I made a compromise, and as I will describe, I made a compromise uh, partly because I was fully conscious that it wasn't clear how you would do the kind of SRM I was talking about. It's now only become clear in the last few days about how I can say how to do SRM even today. Uh, but back then I was in I was in the wilderness, so to speak. So uh, so RM was a kind of compromise setup in order to get things going. So RM was my compromise, uh, which I put out in the mid 70s uh, to facilitate a clear development of a new area. And much earlier in the late 60s, I wanted to impress the mathematicians at the Stanford University mathematics teas by showing how the beloved formal systems of math logic are intrinsic and form permanent fixtures of the mathematical landscape. In order to achieve this, I could not simply start a discussion with a formal system with non-logical axioms. The idea that principal formal systems of mathematical logic are in an appropriate sense equivalent to certain mathematical theorems was clearly envisioned and expressed. For this, one cannot really start with any formal system. Of course, in contrast, RM starts with a formal system right from the beginning, normally RCA naught. We can see my early attempts to carry out this strict reverse math program in the manuscripts available on my downloadable page, these 6 manuscripts. And here, the emphasis of these were not literally the reverse math program. It was a little different. In the first of the above, I wrote in 1969. I discovered a certain subsystem based on a mathematical statement. A perfect subtree was provably equivalent to the weak pi11 axiom of choice. This is before I invented ATR naught, modulo a weak base theory, and the base theory back then was this is before I set up RCA naught or even RCA for this purpose. By the way, I used the base theory arithmetic comprehension, but the emphasis here was on giving in these early documents was on giving a strictly mathematical base theory for the reals for the real-based real analysis and reverse a myriad of strictly mathematical theorems to various standard formal systems in the sense of logical strength. I was mainly concerned with logical strength. Actually, this calibration program with logical strength can be traced back to my publication about the high strength of Borel determinacy in 1971. In a way, the aim of these 6 writings were actually more ambitious than present SRM in this sense. I was talking about treating raw mathematical text. Raw mathematical text proceeds only at most semi-formally. Considerable amount of logical structure is only implied in a raw mathematical text. However, it is possible in the future that needed logical structure could be added automatically to raw text using AI based on appropriate inventory of examples of implied logical structure. This would bring the raw text vision alive. Already by 1974, I was working with the compromise of using a formal system for the base theory with my 2 manuscripts founding RM as we know it today. This paper in the ICM Congress, which, by the way, was based on full induction. And then this paper, which is based on the naughts, putting, the subscript 0 based on restricted induction. these abstracts. And there, I definitely focused on provable equivalences with formal systems. However, I still had the SRM idea very much in mind in Friedman 76. There you see an axiomatization of RCA naught using functions only. Today, the official RCA naught, say in Simpson's text, is based on sets only, and functions are meant to be coded objects. So I propose this as a base theory, but also a strictly mathematical system is in there called ETF, the elementary theory of functions. And I claimed that ETF was outright logically equivalent to RCA naught without proof. And I regard this as the founding operational moment of SRM, even though the ideas were much earlier. So the reason that I made RCA naught, formulated RCA naught, proposed it as a base theory using functions only was because I was thinking of strict reverse math with the system ETF, which is provably equivalent. So the languages, if you have two provably equivalent theories, the languages have to be the same. So that's why I formulated it with functions only. Now, RCA naught with its schemes were readily accepted. RCA naught, of course, has schemes, delta 1-1 comprehension scheme and so forth, a sigma 1 induction scheme for sigma 1, depending on exactly how you formulate it, were readily accepted for RM by the interested researchers. I didn't bother to back up this claim that ETF and RCA naught are equivalent. People shifted to the set version, and they went on to do RM, and they didn't care about strict RM. So I didn't bother do this. But now in recent years, I've been interested in getting the SRM program going. So in this paper, Friedman 21, this 110-page manuscript on my downloadable manuscripts, there's a full proof of this, that ETF is equivalent outright to RCA naught. And ETF is carefully constructed to be allegedly, and we'll talk about this, we'll see, allegedly strictly mathematical. All the axioms are strictly mathematical, are strict mathematical theorems. Or strict mathematical theorems, or maybe I say strict mathematical theorems or facts. Soon after these two manuscripts, the RM program took off mostly using the set version in its current form. And in RM practice, of course, one freely uses coding and functions without even hardly mentioning it. You just learn that you can do this, right? Okay, so let's talk about what strictly mathematical means. Because a lot of mathematicians are not happy with things that are not strictly that are not strictly formal or precise. And logicians also tend to do this. We've always maintained from the outset that although a desired precise definition of strictly mathematical cannot be given in the foreseeable future, the notion can be made precise enough so that a great deal of relevant FOM and rich mathematical logic can be productively motivated by it. Certainly, it is much more precise than notions like important mathematics, beautiful mathematics, simple proof, and so forth. And it's probably true that every one of you have used these words from time to time, right? Without panicking or anything, right? So a precise guide to whether a concept is strictly mathematical can be obtained by counting the number of references to that concept found on the internet. Of course, here one must be searching in and around that concept, not some particular inflexible embodiment of that concept. Another guide is and you know, AI is now pretty good at this kind of flexibility. Another guide is the diversity of the references under various cultural measures. For example, range of a function not only has a huge number of references, but also a great diversity of the sources of those references, namely just about anything everywhere in math. Also, probably in biology also, but that's not what I have in mind as the range of a function. All right, so at this early point in the development of SRM, it is not important to dwell on what strictly mathematical means until a significant dispute arises. But we do need to emphasize that the richer concept of more mathematical, because one wants to make things more mathematical, no matter how mathematical they are, plays an important role, perhaps a more important role, and there one expects even more disputes. However, this is to be expected akin to harder, deeper, simpler, and more important, more beautiful. There's plenty of disputes when you start talking about that. That is in common use in mathematical culture and mathematical literature. Mathematics develops just fine with this murkiness, and so will SRM. All right, so let's talk about how we want to do SRM aimed at the Z2 fragments. So in this section, we'll focus on goals for SRM applied to finite fragments of Z2. We assume the language of Z2 is the official language from Simpson, which is two-sorted and uses 0, 1. It doesn't use the successor function. It uses 0, 1. I kind of like this, actually. 0, 1. At first, I was appalled by it, but now I like it. 0, 1 plus times less than epsilon. I guess equality has to be discussed. Its own equality, when you actually work this out, you have to say equality. Equality is only between terms of sort omega. All right. So I have two ways SRM attacks fragments of Z2. And the first one is too naive. Let S be a notable finitely axiomatized fragment of Z2. We look for a logically equivalent formal system T consisting entirely of finitely many strictly mathematical theorems. We continue to look for alternative T which are simpler, shorter, more mathematical, or more interesting. Unfortunately, none of the commonly studied fragments of Z2 seem to be treatable this way. This is because the language of Z2 is just too primitive to support this with only, based on sets. We modify this goal. However, we're going to modify this goal. However, SRM1 is very much viable if we formulate Z2 with functions of several variables or with sets and functions of several variables. And so I think of this as we want to keep our mind on SRM1 for augmented Z2, in other words, where the language is a bit richer, but we also want one for the official primitive Z2 language, and that's a program 2, that's SRM2. Let S be a notable finitely axiomatized fragment of Z2. We look for a formal system T consisting entirely of finitely many strictly mathematical theorems with an interpretation into S, which is the identity on the language of Z2. This is the key notion. You want an interpretation back, which is the identity on the language of Z2. We continue to look for alternatives that are simpler, shorter, more mathematical, or more interesting. Note that this condition implies that the language of Z2 is contained in the language of S, and that T logically implies S. If you decode exactly what I said. Okay. I mean, I could have put this out in front, but but it actually follows. So we're looking at systems that have a bigger language than the official Z2, logically imply, and conservative in the strong sense of there being an interpretation which is the identity on Z2. In other words, you need that they're saying the same things about the sets. All right. Now, what do I do? That's one kind of SRM, and that's a pretty clear form. But SRM is a broader, I intend it to be a broader subject even. Now, this is already, there's quite a lot of meat in here, especially because of this. In other words, when you actually treat a system of Z2, and I've only carried this out reasonably well for, as you'll see, for the famous 5, but there's a lot of other systems, as we know. So a lot of other notable ones, but it's obviously deeper than even getting one for each for all the systems that one cares about. It's a matter of refining. When you get a good idea, there's usually a better one. So this is quite a significant subject. But let's talk about an even bigger subject, but less careful, less precisely stated or more open-ended. So in the realm of omega-based countable mathematics, we clearly have a large number of notable finitely axiomatized formal systems within Z2, including the famous 5 and much more. We also have a large number of notable finitely axiomatized systems within PA in the realm of Z-based finite mathematics, and that I want to talk about in the second lecture. However, in the realm of real-based real analysis, we do not really have notable formal systems. The closest we come, we just have, idiosyncratic ones according to certain authors. The closest we come to them is through the usual RM systems where reals are treated by coding with rival systems of coding studied. Mathematicians greatly prefer to treat the reals as primitive, not wedded to one particular definition, knowing that there are multiple interpretations, Cauchy sequences, Dedekind cuts are the most famous, and then worry about things and then even on Cauchy sequences, there's the rate of convergence issue. And then worry about things when it's time to worry about things. That's what a mathematician wants to do, which will be never, by the way. So, all this is buried under the rug. Now, of course, they're kind of stuck when they're usually getting salary to teach, and then when the undergraduates come in, and you kind of forced in a good real analysis course to give a definition of the reals. All right, what do we have? What we do have, however, with this arena of real-based analysis, we do have tons of strictly mathematical theorems based on R. In SRM, we take the strictly mathematical approach of treating R as a sort with the ordered field of real numbers as axioms. This will be discussed in the second lecture. This is very different from choosing some particular coding of reals as Cauchy sequences or Dedekind cuts. Those come up when one wants to give interpretations of the mathematical theorems. They certainly play a huge role, but only in the background. It's the kind of, it's in the back room. I will talk about this in the second lecture. Another important area of mathematical wilderness is where we look at mathematics that's proved where there's no clear, tangible, logical principle being used. There's just special arguments and special constructions. Here, the usual non-mathematical elements used in the usual formal systems are just too crude for RM for this wilderness realm. And so you want to do SRM, where the relevant mathematical theorems are taken as stated. So there's where SRM really is, you're kind of forced into it. We formulate the goals of SRM in the wilderness as follows. So what do you want to do in the wilderness? In a rich mathematical realm where there are no generally accepted ready-made formal systems, develop formal systems consisting entirely of strictly mathematical theorems, which provide a transparent logical organization of that rich mathematical realm through logical implications, logical equivalences, interpretations, conservative extensions, and the like. And so we'll be operating in one of the most tamed wildernesses with R-based real analysis in the second half of the second lecture. All right, so now let's get into some specifics about SRM of Z2, SRM of Z2, of the fragments of Z2. So the system ETF, elementary theory of functions, was introduced in Friedman 76. The language of ETF, you have to be careful what the language should be, has four sorts. One over omega, the others ranging over one array, two array, three array functions from omega into omega. I found that the way I did this, trying to be very strictly mathematical, naturally, it was natural to go up to three array. Now we have the constant zero of sort omega, and we use the one array function symbol S on omega. I don't have plus and times, so I can't play Simpson's trick of using one instead of S. And we have equality between terms of sort omega only, with the usual underlying logic. The axiom names are, there's 6 axiom groups, and the names are successor axioms, initial function axioms, composition axioms. The first 3 are very boring, as you might expect, but they're carefully picked to be enough. And that has to be checked carefully. It has been. All right, and then there's the primitive recursion axiom, which is just one single axiom. And then there's the permutation axiom, which is exciting. And then there's the rudimentary induction axiom, which is kind of exciting and very simple. The most exciting one probably is 4. And here's the detailed axiomatization given in section 6 of that paper in 21. It's a slight simplification of the original ETF of Friedman 76 in ways that are documented well in Friedman 21. I think some axiom was dropped and some minor change in notation. I can't remember. It's very minor. So for specificity below, N, M, and R are the first 3 variables over sort omega as they were there. So the successor axioms, remember we have 6 groups. Successor axioms, as expected, because of the setup, you can't get away with eliminating. I think I proved this, but I'm not sure. I'm not sure. You can't get away. You have to put this in because the induction is so restricted. I mean, normally, this is sort of a theorem. You prove this by induction, but you can't. I think here you have to put it in, but it's fine. And the initial function axioms are these boring axioms about the projection functions exist and the constant functions exist. And the successor function. Oh, so S is just a function symbol. So S is not a function constant. And that, by the way, maybe one of the things I might have changed. S is a function symbol. That doesn't mean it defines a function. So you have to add this. See, there are some pedantic formal issues one has to be careful with. All right, then there's the boring composition axioms. And here I had to make sure I had enough. Now, of course, a lot of people just say, well, functions can be defined by substitution, but you can't quite get away. You don't want to get away with, you don't want to do that here. You want to be specific. Um, so these are just special cases of the obvious. And of course, I'm interested in things like, can I make these simpler? Now, once you get hooked on the SRM idea, you want to simplify everything as much as you can. All right, the primitive recursion axiom is done with the parameters carried, uh, and this is self-explanatory. The permutation axiom, the most interesting one of all. Every function that maps omega 1 onto omega has an inverse. And the rudimentary induction axiom, which says you can do induction on f of n equals g of n. The most primitive kind of induction axiom you can imagine in a situation like this. Okay, so in ETF, is ETF strictly mathematical? Well, it's basically obvious that 1 through 6 above are either actually appear in the mathematical literature or are special cases of statements actually appearing in the mathematical literature that are usually stated semi-formally. Like you can define functions by substitution. It's always stated semi-formally in mathematics. In the literature, in talks and so forth. In particular with three, I'm just repeating myself, the usual semi-formally given notion of functions defined by substitution from other functions used extensively throughout mathematics, and 1 through 5 are particularly simple, fairly simple special cases. We can probe more deeply here into exact matches with the actual literature, but this does not seem rewarding, at least at this stage of SRM. I was surprised to see this. I came across somebody actually took this all this seriously. A Russian writes a paper, a preprint on countable strict reverse math, and it's a very nice exposition of the basics of SRM and ETF based on Friedman 21, and shows, among other things, it does a little tweaking that ETF is logically equivalent to replacing the replacing the exciting inverse of permutations by the less exciting functions defined by minimalization, i.e. mu operator. Now, as an example of a more mathematical judgment, the permutation axiom is more mathematical than minimalization. A judgment like this can probably be documented using searches of the mathematical literature. There can be a general protocol for gathering evidence of whether you've done something more mathematical using internet searches and AI. I think that's kind of interesting. All right. Research programs for ETF. So let's take ETF seriously and actually do a little study on it. Although there are a number of detailed questions that arise if we focus intensely on ETF, first two formally precise programs. And you might be appalled by these programs that they're sort of pedantic or whatever, but I really think that if you get into these two programs, you're going to have to develop some very interesting new techniques that might be useful, in other contexts. I think that there's some really interesting stuff kind of forced on you if you want to really get into this. So notice that there are 14 axioms of ETF by counting them. Is this just reverse inclusion? Determine the logical consequence relation among the 2 to the 14 subsets. Now, obviously, you're not going to, this is an enormous table. You're not going to actually build this table, but going to try to explain this or something, do something with this. Is this just reverse inclusion? That's doubtful. That means if I've made these things totally independent, all these axioms of each other, and strongest possible sense. I doubt it. Also consider logical consequence for the many sublanguages of the full language, i.e., one subset proves all sentences provable in another that lie in a given sublanguage. This language, remember, has a lot of parts to it. It's clear what I mean by by a sublanguage, right? Like let's get rid of the functions of three variables, or let's keep only the functions of one variable, and whatever. Obviously, this naturally lends itself to natural partial results. So partial results on program one, uh, rather than swallowing it on the whole. Program two, determine the interpretability relation among the 2 to the 14 subsets of the ETF axioms. Again, this naturally lends itself to natural partial results. We believe that research into these two programs should require the development of some interesting new techniques, like I said. Now, for more flexible open-ended programs, program three, are there alternatives to ETF in the same language that are as strictly mathematical or more so than ETF and are logically equivalent to ETF or mutually interpretable? What if we use only some of the four sorts to do this? In fact, I don't even know how well you can do with less sorts. I think you could do probably pretty well without the three-ary, but maybe not as well. It's not so clear. Anyways, that's an open-ended program. In other words, basically, can you do better than ETF? Actually, I got kind of interested in this, and I'm going to think about this. Maybe I'll be able to say something in the next lecture about that, about making it a little bit better. Nothing dramatic. How can we go weaker than ETF for an even richer SRM targeting more math? Well, in RM, we already started this. A well-known step along these lines in the RM context is using RCA naught star. This system originated in Simpson's book, or that's where I know it from, and has been used as a base theory in a number of articles, including the reverse mathematics of the infinite Ramsey theorem. RCA naught star is the fragment of RCA naught obtained by replacing the sigma 01 induction scheme by the delta 00 induction scheme and adding exponentiation to the language with usable defining axioms for explanation. I'm sure the Simpson was horrified that you couldn't, without exponentiation, you could probably do none of the usual games, like the codings or whatever. So it was sort of added back. Here's some interesting, I don't want to dwell on this, just a list of references. I will make this document available for all of you shortly, so you can see this. So I just compiled some papers using RCA naught star as a base theory. Simpson Smith, these Russians, including including the Japanese, Yokoyama, Ramsey's theory over this. You don't get ACA naught so quickly when you don't have when you weaken the RCA naught. And then the Zafarov-Mumford's book has some stuff in section 6.6. All right, this suggests the use of certain fragments of ETF as base theories for SRM. It appears that RCA naught star corresponds appropriately to ETF with the permutation axiom deleted and the primitive recursion axiom replaced by explanation. Actually, I'm a little bit worried that that's a lie. I'm not so sure about that. That you will be able to recover delta 01 CA when you do this. So I have to think about this more. So it's not clear what obvious fragments of ETF should be used in place of RCA naught star to make it strict reverse math instead of reverse math. Maybe that's not so clear. But anyways, just give you an idea of what something to think about. Now, obviously, there's a good reason that exponentiation was added back in the formalization of RCA naught star. This suggests to see if exponentiation can be proved to be essential for a variety of theorems in countable mathematics that don't directly involve any finite counting. I have a feeling that this derivation of exponentiation in RM could actually be quite interesting. I mean, not that I did anything. I just given a talk, One way to investigate this is to replace the prim axiom by a bounded prim axiom and look for SRM reversals to exponentiation. This plan can also be carried out in RM using a suitable fragment of RCA naught star. In other words, exponentiation may be even more important in mathematics than just counting. Can you make sense of that? In other words, when you do some proofs, you're going to have to build some structures for various purposes that are not counting, and those structures are going to have to include finite structures that actually are exponential size. That's the idea. All right, so now what's SRM? So now we're going to get into SRM for these actual 5 most famous systems of reverse math. All right, so SRM for RCA naught, that we have to start with that. That was the original purpose of ETF. Does ETF actually realize the most ambitious goal for RCA naught? Because it's claimed in Friedman 76 that RCA naught and ETF are logically equivalent. Remember, I said you really couldn't do this kind of thing directly. No, because Friedman 76 was referring to RCA naught formulated with this language and not with our usual this. In other words, what I did in Friedman 76 about the equivalence of these two systems, the RCA naught and ETF, depended upon doing the function version of RCA naught, not the set version, the function version. Then it is equivalent. But now that's what RCA naught really is now. And so we want to be sensitive to this. So for so we have to go to SMR2, remember, with the interpretation. So does ETF handle RCA naught normal, RCA naught set, the current RCA naught? Does it handle it with ETF? The answer is yes, but we have to modify ETF, obviously, to have the language include the target system, right? Remember, okay, so the language of ETF, I call it ETF FS, is ETF with the additional sort of sets and this stuff. In other words, I just import into ETF all the stuff in RCA, all the stuff in our current RCA naught has to be dumped in there. Then we have a system ETF-FS, and the language is just the union of these languages. By the way, these languages have no common symbols except zero. Zero is a common symbol. So, but in general, they're disjointified, right? One's functions, the other's sets. One's epsilon, and the other's application. So we need the additional axioms, which turn out to be quite nice. No pairing issues and garbage like that. Namely, here are the axioms we have to add in order to go to ETF-FS. In other words, modern ETF is still strictly mathematical. That's the whole point. Namely, we add these axioms of arithmetic and the defining less than. But then we have to say that this is, what on earth is this talking about? Because these are new symbols. We have to say that there are two area functions which respectively agree with plus and times everywhere. That's an axiom. And then we have to say that sets and functions are linked properly. Namely, there's a set consisting of the zeros of any given one area function, And there's a one-ary function whose zeros are the same as the elements of any given set. This is modernized ETF. This is modernized ETF. And this is strictly mathematical, just as strictly mathematical as ETF is, because this stuff is totally innocent. Now, from the logical equivalence of RCA naught with functions only and ETF claimed in Friedman 76 and proved in Friedman 21, it's easy to obtain what we now really want. That is, there's an interpretation of ETF FS into usual RCA naught, usual set RCA naught, which is the identity on the language of second order arithmetic. Now that will use, the proof of that will use, that there's pairing functions going on and, that you can handle in Z2 and blah, blah, blah. You see, so there's things get a little more. The back room is more complicated than the front office. We want the front office to be pristine. The back office can be a little bit complicated. That's actually how all businesses operate in the United States, right? Elsewhere. All right, so we'll see that ETF, modernized ETF, provides a way of transferring a lot of RM into SRM. We will illustrate this general transfer by how it works individually for WKL naught, ACA naught, Pi11 CA naught, and for RCA naught as above. However, for ATR naught, the way I do it currently, I have to expand modernized ETF further to accommodate the rationals and just really the ordering of the rationals. I can't code anything. This is SRM for remember. So how strictly mathematical can we be if I don't expand the language? Well, that's an interesting question, and that actually is some difficult mathematical ideas would be needed, I think, for this, to do that. Some tricky at least, mathematical ideas. By the way, you're soon going to see that there's some real reverse math ideas here, some of which are very well are not new, rather than a foundational and philosophical talk, which is all you've been hearing, right? So we'll get to some stuff. All right, so SRM for WKL naught. A good way to achieve WKL naught in SRM is to use our modernized ETF together with the following strictly mathematical theorem in its language. If two functions have no common value, then some set contains all values of the first and no values of the second. It's well known that okay, so here's some famous reverse math. It's well known, I think it goes back to me, actually. It is well known that WKL naught is equivalent to the coded version of 1 over RCA naught. From this, we can easily derive that ETFFS plus 1 is interpretable in WKL naught by an interpretation which is the identity on the language of Z2. And of course, this system is strictly mathematical. So we have now accomplished SRM for WKL naught using this piece of known traditional reverse math. All right, now what about ACA naught? A good way to achieve no, ACA naught. Sorry. In SRM is to use modern ETF together with the following strictly mathematical theorem in its language. The set of all values of any function exists. Or if you like, I could say it better. There's a set consisting of all values of any given f. Okay. Probably a little better way to say it. It is well known that ACA naught is equivalent to the coded version of 2 over RCA naught. One of the early results of reverse math. From this, we can easily derive that modernized ETF plus 2 is interpretable in W. You know, when I prepared this talk, I wasn't totally awake. By an interpretation that's the identity on the language of second arithmetic. ETF of FS plus 2 is strictly mathematical. This is easy. All right, now, I told you we want to do ATR naught last because there's an issue. So SRM for pi11CA naught. A good way to achieve pi1CA naught in SRM is to use modernized ETF together with the following strictly mathematical theorem. Every function maps a maximum set into a subset. So if you have a function, there's going to be a lot of sets, including the empty set, that are mapped into a subset of themselves. And the claim is there's a maximum such. Well, clearly there's a maximum such could take the union of them all. But that's actually powerful. So that's equivalent to pi1CA naught. So with the usual RCA coding, RCA naught coding, pi1CA is equivalent to the coded version of, I just want to say, pi1CA naught is equivalent to the coded version of 3 over RCA naught. The reference I have is me yesterday. From this, we can, I don't know if that's the best reference. I hadn't seen this. From this, we can easily derive that a modernized ETF plus 3 is interpretable in WKL naught by an interpretation, which is the identity on the language of second order arithmetic. Modernized ETF plus 3 is strictly mathematical. Okay, and then we want to
Sorry, that's interpretable in pi11 comprehension. That was another typo.
Yeah. Yeah, I just pieced together the talk, cut and paste and change order around.
Yes, I mean, it's clear what is meant, but just for the sake of posterity, if the notes are available.
I just did it. But I did it by the wonders of technology. All right. Okay. Right. Okay, now SRM for ATR naught. A good way to achieve ATR naught over ETF is to fully modernize ETF, still keeping it strictly mathematical. That's the whole point. Which is ETF FS extended to accommodate the rationals and its order, and I will discuss below what's involved there, together with the following strictly mathematical statement in that language. Any two sets of rationals have an order continuous embedding from one of them into the other one. ATR naught is provably equivalent to the coded version of 4 over RCA naught as proved in this paper of mine. In that volume Reverse Math 2001. So this is the most bare bones version of comparability, because this goes back, comparability of well orderings is equivalent to ATR naught as O result of mine. It goes way back, and then there was some more stuff. I think I wrote a paper with Hurst on things like this, but this is the most bare bones form that I know of. All right, but we've got the rationals in here, so we have to talk about this system. So for this, we easily derive. Oh my gosh. Here we are, ATR naught by interpretation, which is the identity on LZ2. See, we still have that this system is interpretable in ATR naught by interpretation, which is identity on LZ2.
Sorry, what do you mean?
Going to be
that statement about order embeddability? Sorry, or a continuous Could you show the statement again?
Okay, let me go back here. Any two sets of rationals have an order continuous embedding from one of them into the other one. The way I actually formulated it, which is not the simplest, not the logically simplest form, is in the paper, is that it preserves limits.
But do you mean an order preserving embedding?
Yeah.
Because for example,
No.
if you take omega squared and the integers.
No. I've got the book over in the next room. No, I've got it right here. Order continuous. See, this is in the context of a paper in which I do it for metric spaces. You see, it's a special case of the statement for metric spaces. So it's order continuous, not preserving.
So what you mean is order is continuous with respect to the order topology.
Yeah. Right. Yeah. And there's a stronger theorem that this is true for metric spaces, but the point is the reversal. And metric spaces is like light years. I mean, that's now serious. That's serious SRM to get up to metric spaces. Now you have to really be building up strict mathematics. So we definitely want to minimize the dose here. So this is just rationals. Yeah. So this is a paper. This is a pretty detailed paper here in this volume, Reverse Math. Yeah. All right. See, I told you there'd be something in this talk other than philosophy and foundations. All right. So, now let's talk about how do I document this system. Now, in order to document the strictly mathematical system to support this, we have to do this. This illustrates the spade work that needs to be done far more elaborately in the proper development of SRM. Since different researchers may do such spade work differently in the details, we need to have an official SRM website, which tracks the needed extensions of the needed extensions of modernized ETF that arise to support SRM. It tracks official, strictly mathematical extensions of ETF SF so that all SRM researchers are on the same page. Right now, nobody cares. By coding, blah, 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 and do it any way you want your students to do it, have to do it. It also contains, but now we're talking about strict reverse math. It also contains statements of SRM results with references to their proofs. This needs to be run by a committee, the SRM committee. When introducing the rationals, see, because people will do different setups, though, you can imagine that, your way of setting this up and my way of setting this up is going to be different. So introducing the rationals into modernized ETF, it's probably best to introduce the ordered ring of integers first, and then the ordered ring of rationals second. I like this hierarchical way, with Z and Q as separate sorts. And let's first focus on the ordered ring of integers. What would I do? A lot of sorts need to be added. Adding the ring of integers can be construed as a special case of adding a structure where the domain elements are structureless points like your elements in set theory. Whenever a structure is added, one also adds a new sort for its domain. But then we also need to add new sorts for the 1, 2, 3 array functions from various of the sorts into various of the sorts. There will be some special functions between sorts like absolute value from Z into omega. And also identity from omega into Z. this has to be worked out so that you do put, there's always a danger that you don't put down enough stuff. So, and so I'm not going to take this further. I'll take this further somewhat in the revised version of Friedman 21. And let me close by just a list of notable fragments, which surely aren't complete, where we want to do this, we want to attack with SRM. And we need to do some more. We have to do more than what we've done here. I mean, obviously, if you take one of the famous five and you add a mathematical statement to it, you've already solved it, because you do the SRM of the you do the SRM of a notable system and then add them and just carry the mathematical axiom over if it's like that. So there's a lot of systems people consider that have components that are strictly mathematical or coded. But these are the ones these are some of the ones, maybe all of the, maybe nearly complete, I'm not sure. A list of ones you want to attack with SRM that are not included. See, RCA naught is more than that. You see, has more stuff than that, so forth. Okay, so I think that's all I want to say today. And I'll say more in the second lecture in the different contexts. Thank you.